Very, very active research. Please take it away.
Yeah, so thank you very much again for the invitation. Thanks everyone for being here. Of course, you can stop me at any time. So my voice is kind of flat. So if you don't ask me questions, you're all going to fall asleep after half an hour. So today is the first lecture. The title that I was given was a bit long, so I'm going to shorten it to light and bright. We will see why. The course of the lectures, we're going to talk a lot about light particles coupling to photons, but also bright new ideas to solve old problems using light and weakly coupled particles. So I will start a bit philosophical. I know it's not to the taste of most physicists, but okay, when you work on something or give lectures on something, you should obviously ask yourself how you're spending your time. So why would you want to work on light and weakly coupled particles rather than anything else? I mean, every paper is a big investment of your time and energy, and so you should really be convinced of what you're doing when you embark in a new field. And so we are all kind of guided by this desire for minimality. Even if we don't think about it often, most of the stuff we do feels better when we're not adding too much stuff to the theories that we already know. And this is, in some sense, of course, completely arbitrary. It comes from the shape of the human mind, in some sense, but nature never promised us to be simple and minimal. And if anything, I mean, if you have, for some reason, a belief that string theory is describing quantum gravity, it's actually surprising that we see so little stuff at low energy. It's even more surprising that we don't see any more than the standard model also in cosmology. So we measured the Hubble parameter that tells us how fast the universe is expanding at different times in the history of the universe. And this object, as we will see more precisely in the course of the lectures, is a measure of the total energy density floating around in the universe at any given time. So even if there was something that was completely decoupled from us, but only had gravitational interactions, we should see it. So to me, it's a complete surprise that this object is essentially exactly the same as what's predicted only in the standard model for many decades in energy in the history of the universe. And so if you want, this is a puzzle that could be easily explained if most of the stuff coming from high energy compactification was light or weakly coupled to us. However, this is kind of a very broad stroke justification and is not giving us anything concrete to work on. Also, in some sense, is an abstract puzzle that doesn't have a connection with anything observational that we cannot explain. So really, for me, the motivation to think about this kind of light and weakly coupled particles, other than this general puzzle, are a series of questions that we are asking about nature and we don't yet understand, which are mostly observational. The first one is dark matter. So as you know, there is some stuff that makes up about 80% of the matter in the universe, about a quarter of its energy density today, and we have no idea what it is. But as we will see also today, we know that in some sense it must be weakly coupled to us. And this, we will see that leads us to think about some specific kinds of light and weakly coupled particles. Another reason to think about them is that there is an operator in the standard model that we don't quite fully understand. And it's the antisymmetric contraction of two gluon field strengths. So I'm going to just write it down very explicitly. And so the object in front of this operator has dimension 0 in energy, which means that in principle can get contributions of order 1 also from very high energies. And whatever is coming from high energies in low energy observables, let's say that our experimental energy is E experimental, will leave traces that are suppressed by some power of the large energy, sorry, some power of the low energy divided by some power of the large energy. This is just a general consequence of a decoupling theorem in quantum field theory. And so it might look like something very weakly coupled at low energy. Yet another reason that Gilad told you about this morning and will keep telling you about is the hierarchy problem. So traditionally, we were 100% sure that the Higgs boson mass was explained by dynamics close to the value of the mass itself. Today, we are not that sure anymore. And there are a lot of creative ideas floating around that involve light and weakly coupled particles. And unfortunately, I'm not allowed to talk about them, but Gilad will. Finally, okay, there is, if you want, the general top-down motivation from string theory for a few of these particles. Let's say, especially for the Axion and the Dark Photon. And finally, okay, my least favorite is just that there is a lot of empty space out there. So, I mean, if you just want to know what mankind has probed in a plane of coupling versus mass, there are huge regions at small coupling and small masses comprising hundreds of orders of magnitude that are still completely unexplored. To my taste, the good reasons to think about these objects are 1, 2, 3. So concrete problems that have an answer that point to them. But, OK, I think we should not discard also the last two more general motivations. However, OK, in this first, I don't know, 10 minutes or however long I've taken, I've kind of fooled you because I keep talking about light and weakly coupled particles, but you should have asked me immediately light and weakly coupled with respect to what? Because, I mean, without any frame of reference, it doesn't make sense to call them light and weakly coupled. And, well, the simple answer is that people colloquially talk about light and weakly coupled particles compared to the energy frontier, so compared to objects that are order 100 GeV and they have couplings that are between 1 and 0.1. Or if you want to be more, let's say, model independent, we talk about light and weakly coupled particle with respect to the electroweak sector of the standard model, where particles have a mass of order 100 GeV and order 1 couplings. However, I mean, I like to think about light and weakly coupled more in relation to the answers to these questions. So we will see, especially in the first case, that there is an answer to what dark matter is, which is, again, comparable to the electroweak sector of the standard model. And then we will see that there are equally good options, which are exponentially more weakly coupled and exponentially lighter. So you can think about the titles of these lectures both in connection to traditional answers to all problems or as a comparison to the electroweak sector of the standard model. And in the rest of our time together, well, I will talk mostly about these two. So dark matter and what is called the strong CP problem. So I didn't tell you exactly what we don't understand about this operator, but an entire lecture will be about that. In short, this parameter theta, we expect it to be order 1 from symmetry, but we measure it to be smaller than 10 to the minus 10. So it's a problem that's similar to the puzzles surrounding the Higgs boson mass in a precise sense that we will see in the near future. OK, so as I said, most of the lectures will be on these two problems. But before getting to them, I think I should do justice to the title of the lectures by giving you a little bit of zoology, so some of the options in this realm of light and weakly coupled particles that people think about the most. And I want to do it by trying to answer a question. So the question is kind of simple, so I asked it to myself when I started preparing the lectures, and then I found out that my intuition was completely wrong. So the question is, are lighter particles easier to detect? Well, this means that you can see smaller couplings with respect to an heavier particle, if you want to be precise. And so, well, like you will see as you get older, you will have some feeling for the answer to a question, but you have no idea of where that feeling is coming from, and then you have to force yourself to be more concrete and write down the equation. So, okay, so I don't want to tell you what my feeling was. I want to know from you if you want to try to answer. So do you think the answer is yes or no? Anyone wants to be, maybe, okay, if no one wants to be brave, you can raise your hand if you think that the answer is yes.
I would say that it depends on the technique.
Sorry, it depends?
It depends on the technique that you want to detect.
On the particle or on the experiment?
Yeah, I think both, because sometimes depending how you develop your model, and how do you prepare the experiment, the technique itself to detect it.
Okay, so I'll collect a few more answers and then I'll tell.
Very difficult. For example, primordial neutrinos, the temperature is more or less 1.9 kelvins, and the vector is impossible in this moment.
Okay.
Right?
Any more? Okay, yes.
So we have experimental bounds that kills multiple theories, so that's very hard to beat. And we also, so neutrinos also are very far, but if you think something that looks like an electron, you will have a lot of background also.
Okay, so you all kind of gave the right answer, which is that the answer is both yes and no. It depends on what particle you're looking at. But my feeling when I asked myself this question was not so nuanced, let's say. So I thought, okay, of course, lighter particles are easier to detect because you can just do this. So roughly their cross-section will be something like that, just from dimensional analysis. You can also get the coupling from dimensional analysis if you restore units of H/. So, okay, I mean, clearly, on average, lighter particles will be easier to detect, so you will see a smaller coupling. Of course, this is not true, as you pointed out, and we will see a few examples of why it's not true. So let's start with spin zero scalars. So it's not true, but it's also true. So we will see in what detailed ways it's both true and not true. So for spin zero scalars, you might think, okay, this is correct, except that there is a naturalness bound on the coupling if you want their mass to be technically natural. So you roughly expect something like this, where lambda is the largest scale where your theory is valid. So naively, this completely nullifies this very simple argument. However, if you're looking at a spin zero scalar, there's a couple of non-relativistic, non-trivial effects that indeed makes lighter particles much easier to detect. The first one is that, a non-relativistic particles just from quantum mechanics will be localized roughly in a region of order lambda of its de Broglie wavelength if its momentum is q. So this is going to be something like this. So if you're asking how these scalars, these very light scalars are interacting with a material, you have to sum coherently over all the particles within a de Broglie volume. So if this object is really very light, so that its de Broglie wavelength is bigger than the slab of material that you're looking at, then, well, the probability amplitudes sum coherently. So you're going to have something like this. So the total probability amplitude for the particle interacting in this material will be that of interacting with a single particle in the material times the number of particles in a de Broglie volume, where this is the density of the material. And so your cross-section can have an enhancement that's potentially huge. Because if this object is macroscopic, then this n can be Avogadro's number. If you had a particle whose de Broglie wavelength was smaller than the interparticle spacing in the material, so the distance between these two dots is the interparticle spacing, then okay, it could still cross a macroscopic region. And let's say that in these macroscopic regions, there are still MP particles. But in this case, the interaction would sum incoherently. So you would lose a huge factor of n compared to the lighter particle that's spread over the whole slab of material. The second reason why these spin zero scalars might be easier to detect at low energy is because they can, in principle, mediate long-range forces. So for instance, if you look at a Yukawa interaction, and and you compute something like this with a phi exchange, then, okay, you can compute the matrix element between these two states of momentum P prime and P of your transition probability. So essentially the S matrix minus the identity. And you're going to find something like this. And if you remember, like your quantum mechanics courses of scattering, this is nothing but the scattering potential. So you can ask, what's the position space equivalent of the scattering potential in momentum space? So you can take the Fourier transform of this object, and this is going to tell you roughly what force this scalar is mediating at low energy, non-relativistically. And okay, we're not going to do. Is there? Okay. We're not going to do the integral here step by step because we don't need to. So we can use some intuition from complex analysis plus dimensional analysis to get the result. So first of all, the integrand as poles only on the imaginary axis, so at I and phi in Q. So where this is the magnitude of Q. And so if we do this integral by closing the contour up, we're picking up this pole. So we're going to have an exponential factor that looks like this. Can you see everything that, okay, maybe, can you see everything that I write? No, okay. So I'm going to write it, and I write it here. Okay, so you're closing the contour up, and you're picking up this pole. So your exponential is becoming e to the I, value of Q at the pole, times distance. So roughly e to the minus m phi distance. And then you can estimate the rest from dimensional analysis. So you have a Q cubed divided by a Q squared. This is a Q, so a 1 over R. So your very rough estimate of this integral is e to the minus m phi R divided by R, which is also the correct result modulo order 1 factors. And so this is telling you that the lighter the particle becomes, the longer range this force has. And this, of course, is another thing that can help you detect them. So if you, for example, can measure distances with some finite absolute precision, and this particle is light enough, you might want to measure the distance difference that this is inducing between the Earth and the Moon. So you have a baseline distance that's very long, and even if this particle is inducing a relatively small effect, your absolute precision might be enough to see it. Okay, so for the spin zero scalars, we've seen arguments in both directions. So the naive answer that I gave initially is not correct because of this argument. But there are two more reasons. The first one, the Broglie coherent enhancement, and the second one, these long-range forces, that might actually make it much easier to detect a light scalar compared to a heavy scalar. However, already if we take one step beyond the spin zero CP even scalars, and we look at spin zero CP odd scalars, the answer is not the same anymore. So in this case, we wrote down this Yukawa interaction. In this other case, if we don't want to break CP, we have to write down this other one. And this interaction is coupling to mass. So if you ask what's Q bar Q in a material, this is going to be proportional to the total mass in your sample. So it's very easy to prepare a sample to which this scalar is coupling coherently. You just take a slab of whatever you have in your lab, and if the scalar is light enough, it will see this huge NP squared enhancement in the cross-section that we were saying before. However, for the CP odd scalar, it's not so simple, because if you take the non-relativistic limit of this fermion bilinear, you get that this CP odd scalar is coupling to spin. So these X's are two-dimensional spinors, sorry, so they can be either 0 or, so they are these guys. And then, at low energy, the only thing that survives is this term. So the scalar is coupling to the spin of the sample. And it's much harder to polarize coherently a big slab of material. I think the best we can do now is having order, I think, 10 to the 21 spins per centimeter cube in samples that are of order a centimeter cube. If you compare this with what you can do in this case, which is take 10 tons of material and just put them there are many orders of magnitude. And this makes a huge difference when you're trying to detect one particle or the other. Finally, okay, I'm going to give you one more example, and then we're going to conclude with this zoology, which is by far my least favorite part of the lectures. But this gave you an idea, at least, of the kind of challenges that people are facing when trying to see these particles. So let's move one step further and think about spin 1 objects. And so one classic incarnation of this type of particles in the light and weakly coupled regime is the dark photon, which is kinetically mixing with the ordinary photon. So you can write a Lagrangian that looks like this, where F refers to the photon and F prime to the dark photon. And the photon couples to the usual electromagnetic current. And we can, if we want, give a mass to the new photon, and possibly also a coupling to some particles in its own sector. Okay? So the typical thing that one does to work with this Lagrangian is to diagonalize the kinetic term, which you can do relatively simply at order epsilon squared by the following transformation. So this transformation at order epsilon squared is gonna give you this Lagrangian down here. So I'm then gonna abbreviate the f mu nu by f squared. I think it's clear what's going on. Okay, and then the part with the dark photon remains exactly the same. So now where is the interesting part? So the interesting part is that let's imagine that that the mass of the dark photon and the coupling of the dark photon to its own sector are both 0. So in this case, you can make a second transformation, which I'm going to read up because I forgot. And the second transformation, well, I should have remembered it because it's kind of trivial, but it's this one. And you can see that this is a rotation. It's orthogonal, at least at order epsilon squared. So this is the same as having cosine of epsilon minus sine of epsilon, cosine of epsilon plus sine of epsilon, and expanding it. So this is not doing anything to the kinetic term, but it's setting to 0 the interaction of the dark photon to us. So if you do this transformation, you're going to get the same kinetic term, and here only one photon coupling to us. So if the masses and the coupling to the dark sector are 0, you have no effect. So only the ordinary photon is coupling to us. This means that also in this case, even if by looking at the Lagrangian it's not obvious at all, when the mass goes to 0, also the coupling of this particle to us is going to 0. And well, in a non-trivial way that we've just seen. So if we were to turn on the mass or the coupling to the dark sector, then this transformation would, yes, leave invariant the kinetic term, but would introduce a mass mixing or an interaction of our photon to the dark sector. So we could still tell that a dark sector exists. And well, I was always confused by these changes of basis until I started thinking about it as a two-dimensional plane. So if both these objects are 0, you have only one direction in this plane, which is given by your current. So you can always rotate the axis in such a way that only one guy talks to this current. But if you turn on any one of these two, then you're introducing another vector in this plane. And now, no matter how much you rotate the axis, if these angles are different, you can never make only one couple to us with no other effect. Okay, so this concludes the zoology part that I did mostly to give you a lightning overview of the bosonic particles that people think about most of the time. But now we can keep my initial promise and focus on the motivations. So start asking the questions, seeing what answers come out, and we will see that some of these answers will point to light and weakly coupled particles, and I will also tell you about the traditional answers, so you can judge for yourself which one you like the best. Okay, so and I'm going to imagine that you know almost nothing of cosmology and thermal history of the universe, modulo what Jay told you last week. So if I'm going too slowly, please stop me, because I think I have like 4 times more material than I can cover. So if I can skip something, it's only good for all of us. Okay, so we're going to start with dark matter. And well, I like those lectures on dark matter that start with a list of what we know about dark matter, because it's not that much. And it immediately tells you, I mean, what kind of problem we're facing. By the way, am I supposed to stop halfway or just keep going? Okay. No problem. Okay. Am I already halfway, by the way? Yes. No. Yes, okay. Not yet, okay. All right, so, yeah, because I'm page like 5 of, I don't even know how many, but. All right, so what do we know about dark matter? So the first thing we know is that it interacts with gravity. Otherwise, we would not have seen it at all. Second thing we know is that it's long-lived, so its lifetime should be at least longer than the time it took the universe to get from matter radiation equality until now, which is about almost its old age, so it's 13 billion years. But in reality, for certain kinds of dark matter, which can decay into products that we can see with satellites, the bound is much stronger, like 11 orders of magnitude more than the lifetime of the universe, or something like that. This is the bare minimum. Then we know that it's dark, hence the name. And it's dark means that its interactions with photons are small compared to those of other standard model particles we know. So it's roughly 10 to the 12 times smaller, this cross-section, than the one that you would have for an electron. And so here you already start seeing where the weakly coupled is coming in. But in a few more hours, you will see it much more precisely. Then, OK, we need it for the CMB. So to explain what we see in the CMB. Essentially, you know, you've seen last time this plot of the power spectrum versus the angular mode on the sky. It has all these wiggles and all the points following very precisely the wiggles. So if dark matter wasn't there, this whole thing would shift by a macroscopic amount in this plot. So it would be a many sigma disaster for the CMB if dark matter wasn't there at the time of matter radiation equality. So another thing we know is that it does not form disks. So only about 3 to 5% of dark matter can be in disks that are roughly the same size as those where we see the baryons in our galaxy. Then we have a mass range. So the dark matter mass has to be heavier than 10 to the minus 21 electron volt. It has to be smaller than 10 to the 48 GeV. So as you can see, we have only 80 orders of magnitude in mass where to look for it. And the lower bound comes from its de Broglie wavelength being 1 over the mass times the velocity. And the velocity inside galaxies is essentially model independent. It comes from virialization due to gravitational interactions. So galaxies have existed long enough to be in equilibrium, and the equilibrium velocity is roughly 10 to the minus 3, the speed of light. So the dispersion of the dark matter velocity. And this gives you the Broglie wavelength for dark matter, which is roughly a kiloparsec when the mass becomes this lower bound. And a kiloparsec is the size of a dwarf galaxy. So if this object was lighter, we wouldn't see the dwarf galaxies that we see. There's also a bunch of other constraints, but this is the most robust and intuitive. So if you're interested, I can give you some references about the other constraints, but this is already enough. And up here, there are bounds from lensing, right at this mass. Then there are others at even higher masses, but the short version of the story is that dark matter there is so big that you would see it in the galaxy. It would lens stars that are far away from us, but still close enough to us. If it's even bigger, it would destroy neutron star binaries and do all sorts of stuff. There is a range in which it distorts the CMB, but so essentially above this number, there are many different bounds. The one that really is pushing it here is lensing inside the galaxy. So then we know also that itself interactions are constrained by about another 100 orders of magnitude, because sigma, so the cross-section for itself interactions over mass, is about centimeter squared over gram, so it should be smaller than this from a series of observations. But the smallest that itself interactions can be is gravitational, so it's 10 to the minus 21 eV squared over m Planck squared. And if we translate that number in particle units, it's roughly 10 over GV cube. So you see that dark matter in the just below the GV range can have order 1 self-interaction couplings, but it can also have only gravitational couplings and be this light, and this leaves you roughly 100 orders of magnitude open in the possible self-interactions that dark matter can have. Then we have comparable bounds on the standard model couplings. So again, they could be only gravitational, so have some effective coupling for their, say, 10 to the minus 66, but they could also be geometric. So if dark matter is this big, it could interact with anything it touches, so order 1 couplings or more. And so here, again, we have about 67 orders of magnitude open. So what else do we know? Let's see. Well, we know a couple more things. So we know that dark matter is either warm or cold, and this is something that I will explain later. Essentially, for the experts, its free streaming length should be smaller than a megaparsec. Then we know how much dark matter energy density there is in the galaxy, and also how much there is in the universe, which is roughly about GV over meter cube. So this is galaxy. And finally, we know one more thing, which is that if dark matter is a fermion, it cannot be lighter than a kilo-electron volt. And this is quite cute because it's one of the very few examples I know where classical physics and quantum mechanics play at the same scale. So essentially, if you have a, say, ensemble of particles of density rho, you can compute their Fermi velocity. Okay, so, and let's say that the density depends on the distance from the center, as it's the case in a galaxy. Then the Fermi velocity of this group of particles is going to be the following quantity. But if this velocity is bigger than the escape velocity of the galaxy, so this is quantum physics, if you want, quantum mechanics. But then you want this to be smaller than the escape velocity of the galaxy, which is purely Newtonian gravity, so classical. The galaxy doesn't form. And interestingly, there are dense enough and small enough objects that this gives you a bound on the mass of fermions to be dark matter that has to be larger than a kilo-electron volt. Okay, so so why did I make this shopping list? Okay, some of the items are here just for completeness, so that you know all we know about dark matter. But some of the items should give you pause and give you a sense of what's the best way of trying to understand what's dark matter. And these are items 6, 7, and 8. So I emphasize that there is a huge parameter space in front of us. So many orders of magnitude that there is no hope that we can completely cover it experimentally, even if the children of the children of the children of our children devote all their resources just to that. And this should have been made even more poignant by my first example. So even just going from a spin 0 CP event scalar to a spin 0 CP odd scalar, it changes completely the kind of reasoning you have to apply. So the difficulty is not just sheer orders of magnitude, it's also qualitative. So for each one of these hundreds of orders of magnitude, you typically have to have a new idea. So since, okay, my lifetime on Earth and in physics is presumably limited, although, okay, I've heard of some exciting developments about immortality, what I want to do is maximize my chances of picking out the right slight small corner of parameter space to look at. And so I think that that's why dark matter theory, even if in latest years has been a bit disregarded, is extremely important. So what are the best candidates that we have? The ones that we attach the highest probability to be there. That's where we should start searching, or that's where we should start working. Because otherwise, essentially, we're guaranteed not to find it if we just throw darts at this gigantic parameter space. And so that's what's going to come next. So I've already essentially spent half a lecture only on the introduction. But OK, now we can move forward and see what are the best answers to this question that check all the boxes. And I'm going to start by telling you the standard story. So I'm going to tell you why weak interactive massive particles have been looked for decades, have attracted all theoretical attention also for decades, because they are really a fantastic candidate. And then after that, I'm going to tell you how some very light and weakly coupled particles compared to them, I think, match up the level of theoretical appeal. And OK, to do that, we need to talk about the thermal history of the universe. So I'm going to use some of the stuff that Jay already told you about. So I'm going to skip over some parts. But OK, this course is as self-contained as possible. So I'm going to tell you what it means for the universe to be in equilibrium, what are the consequences of this equilibrium for particle production, and why it's so easy to imagine that dark matter is a 100 GeV particle with weak interactions to the standard model. And so, OK, I said that the introduction was over, but now there is a second introduction to thermal physics in an expanding universe. Yes?
Professor, could you please comment again about this velocity information? Like, how do we get it?
This one?
Yeah.
Yeah, so essentially, this comes from the fact that dark matter is interacting gravitationally inside the galaxy. So essentially, so this upper bound on the self-interactions is telling you that, that self-interactions are not so important for reaching equilibrium inside the galaxy. And so as galaxies started to form, matter started falling into this potential well. So more and more matter fell in. But at some point, OK, all the matter that was close enough fell in. And they started orbiting each other and reached equilibrium. So this is, in some sense, the end result of the equipartition theorem. So you started with some potential energy, and you ended up with some kinetic energy. And so this is the prediction for a galaxy roughly the size of the Milky Way, but it carries on very similar also to these dwarf galaxies. Anything? Yes.
I have two questions. Which is you mentioned the dark photons, okay?
Yes.
But which is the great motivation for dark photons? And the second is dark photons or dark bosons in this case imply necessarily new force in the nature?
Okay, so to question one, well, I can tell you what are the motivations, then you can decide if you think that they're very good or not. Well, one is that they could be dark matter. The second one is that it's easy to get them from string theory compactification, so you usually expect them to exist from that. But that's it. So it's not that they answer like in an especially nice way any of those questions that I listed at the beginning. If you have a new boson, you typically have a new force in the sense that I did before. So if you just compute the matrix element of 2-to-2 scattering of matter, you get something like what I showed you before, and that's true both from spin 0 and spin 1. But it could be so short range that we don't see it as a force, really. For example, so it depends. So if their mass is small enough, we see it as a long-range force like electromagnetism. If it's small enough, we see it as such a short-range force that it manifests itself differently. Like weak interactions don't look like they're pulling objects together, but they still, I mean, the calculation of the matrix element is still the same. No problem. Anything else? Yes. Yes.
You told that this coming from this potential well that created by TM particles, not the unique. But today's there are galaxies and there this there are weakers there and we have some density profile there. So it is something called core crust problem. So hot DM and warm DM also contribute some fraction of dark matter, right? So their velocity average could be some different value.
So yes, so this velocity is, well, so first of all, it's a standard deviation. So there is a probability distribution for dark matter velocity inside the galaxy, and it follows Maxwell. So it's roughly this, and so the sigma square here is what you have here, okay? So it's really a velocity dispersion. So there could be small deviations from how the profile looks like in the center. So of course the velocity is not going to be the same at every point. So depending on the profile, you'll see a different velocity. So indeed, in different shells around, that's one way in which dark matter was seen. So the radial velocity of stuff going away from the center of the galaxy was changing. So of course, depending on the exact profile, you will also have a slightly different velocity. This is a number that's valid on average for most galaxies. Yes?
This upper bound on mass
Yes.
corresponds to what theories? Where dark matter is made of black holes?
Typically, yes. So you can imagine that's either made of primordial black holes or other compact objects that can come, I don't know. Let's say that in a dark sector you have a long-range force like the one I described. Then dark matter could clamp and form objects like planets that we see in the observable sector. And this would be, this is roughly the mass of Pluto. So it could be a planet-like object, or it could be a primordial black hole. Yeah.
Isn't the lower bound on the mass there kind of restricted for massive electric field?
For massive, sorry?
Electric field.
You want to know if it's different, or?
No, I mean, isn't it kind of restricted?
This one?
Can
Not by much. So it's debated whether it's 10 to the minus 22 or 10. So there is a range of bounds going from 10 to the minus 22 to a few times 10 to the minus 21. But as far as I know, the spin is not changing much. So in some sense, I mean, here, it's something simpler that it's going on. So if this particle is too light, you cannot localize it better than the size of a galaxy. So in some sense, it's a very robust bound that applies to everything, except fermions, which have to be even heavier. More questions? Yes.
So you just said this is the bound for us to measure this kind of particle, or is this the bound for us for this to exist at all?
So this is an experimental bound coming from the fact that we've observed these galaxies that are kind of small. No more? Okay. So now okay, let's see how we could produce something that respects all these requirements. So as you know, if you look on scales bigger than 100 megaparsecs, the universe looks homogeneous and isotropic, so translational and rotational invariant. You also know that the universe is expanding, so if you take 2 points, A and B, at some distance, and you measure their velocities, these become bigger and bigger as you increase the distance between the points, and this proportionality factor is known as the Hubble parameter that astrophysicists like to measure in these units. And finally, you also know that early on, so at the time of the CMB, when the universe was 1,000 times smaller than today, but almost 13 billion years younger than today, it was very, very homogeneous and isotropic. So the differences in energy density point by point were just 10 to the minus 5 of the total energy density. And so you need a description of the universe that has built in all this experimental knowledge. And you've seen already with J that this is the FRW metric, so the Friedman-Robertson-Walker metric. So this object describes a translationally and rotationally invariant universe, but also a universe that can evolve. So this time-dependent scale factor allows you to have a universe that's almost entirely homogeneous at some time, but today, when you look at it over scales that are much smaller than 100 megaparsec, becomes non-homogeneous and non-isotropic at all because you have galaxies all over the place. And so, okay, the first question that you need to ask in such a universe, even before worrying about dark matter, is how this parameter evolves. And well, the answer is known. You just have to solve Einstein's equations. So you write down the Einstein tensor. And so depending on the value of the stress energy tensor here, you're going to have a different answer for the scale factor. So the components of the Einstein tensor will depend on the scale factor, and the energy density in your universe is going to tell you how it evolves. So what can we say about this object in our universe? So, well, our universe is a collection of particles, so you might want to start with one particle. So for one particle, this is the answer. So for one particle, this is an object that has support only over the trajectory of the particle. So this xp of t describes how the particle is moving. And then it has this p factor. And as an exercise, you can derive this from a single particle, for the single particle action. Okay, so now that we have this object, we want to incorporate the fact that in the universe there's not one particle, but many of them. And there are so many that it's totally fair to go to the continuum limit. So the total stress energy tensor for the universe is probably going to look like something like this. And this little n is the number of particles per unit volume. So the 1 over volume is the continuum limit of this delta function. And you might wonder why I could write it like this without even thinking. And the reason are the symmetries that I told you about at the beginning. Since it's translational invariant, n cannot depend on the space-time point. So anywhere you are in the universe, you have the same n. So there is no x here and no integration over x. Since it's rotational invariant, it can only depend from rotational invariance, so only on the magnitude of the only vector that you have, and that's it. So you're just summing over all possible particles by doing this. And this object is much simpler than it looks when we write it this way. So first of all, you can see immediately that if you have any of the off-diagonal components of this object are 0. Because if you write them down explicitly, you're going to have some odd factors of momenta times some functions that are even in all the momentum components. So these two functions are even, these two objects are odd, and you're integrating from plus to minus infinity, so you get 0. Okay, so this already makes our life much, much easier. What are the diagonal components? So we have T00. Well, T00 is very easy, because you're essentially just have an energy integrated over a number of particles over volume. So this whole object has the dimensions of a number of particles over volume. So this is going to be a total energy over a volume that we're going to call rho, so the energy density. The other components are a bit more complicated, so by just looking at them, one might not guess immediately what they mean. And so, well, I'll give you a simple argument as of why these objects are just the pressure, and they are equal for all three components. So imagine that you have a cube of size L with many particles inside. So if you have a particle going from one side to the other and then bouncing off elastically, there's going to be a momentum exchange with the wall that's going to be twice the momentum of the particle. So this is the particle velocity in the I direction, and this is just twice the momentum that it had because it bounced back. And to travel between the two walls, it took it a time (2L) divided by the velocity. So if you ask what's the force per unit area that this cube is experiencing, it's just the momentum exchange over the time over L squared. And so finally, it's m vi squared gamma divided by L cube. And if you multiply the numerator and the denominator by m gamma, which is just P0, then you're going to get exactly what we have in our integral. So a pressure is nothing but this pi squared over P0 over the volume, which is what we have here. So we're going to call these components the pressure. So finally, our stress energy tensor in the rest frame of this ensemble of particles is very simple. It just looks like this. Okay, and well, this derivation, you don't see it often, and it always bothered me to just see people write down the stress energy tensor like this. So even if it's a bit basic, I wanted to do it for you. And now, okay, we can connect with what you've already seen from J. So now that you know T mu nu, you can rewrite these equations in the usual form, so in the form of Friedmann equations. And here I forgot the normalization, so I'm going to check. Okay, so now in principle we know how A evolves, but we still don't know what are rho and P. And this is where the new part comes in, so something that in principle J did not tell you about. So how do we determine rho and P? So we know experimentally that the universe was in thermal equilibrium at least at a temperature of 1 MeV. So the universe looked like a standard model thermal bath at that temperature. And we know that because we measured light elements in areas of the universe where there are not many stars. So we measure like lithium, helium-4, deuterium, et cetera, et cetera. And in these regions of the universe, these elements cannot come from stars or anything happening late in the history of the universe. They can only come from what's called Big Bang nucleosynthesis. So essentially, at these very early times, when the temperature of the universe was 1 MeV, these nuclei were produced, and they stopped interacting with the rest of the standard model. So whatever amount you made at that time stayed there until today. And the calculation that can be done for a universe in thermal equilibrium with just the standard model corresponds exactly to the amount of this stuff that we see today in areas of the universe that are poor of stars. So our working hypothesis is starting from this observation, so that the universe was in thermal equilibrium at a temperature of 1 megaelectron-volt, and was essentially described by the standard model. And okay, from a megaelectron-volt to today, we can just evolve it using the equations that we know, and all the observations that we made at lower temperatures, like the CMB, are in complete agreement with this picture of thermal equilibrium and evolved with the equations that we know. Going above in temperature, we have to make some assumptions. So if you consider it reasonable, we can imagine that the universe was still in thermal equilibrium with larger temperature. But, okay, as we keep going higher and higher in energy, at some point, we don't even know the fundamental theory of particle interactions at those energies. We can considerably quite conservatively extrapolate at least to 100 GeV, where we know the standard model. Beyond that, there might be new stuff. We don't know for sure. But, okay, it's conceptually, we're making an assumption by going up. In practice, experimentally, we don't know if the universe existed before a mega-electron-volt in thermal equilibrium or not, but it's an assumption that most of us are willingly to make, and it's not considered a huge assumption, but it's important to point it out. Okay, so independently of what assumptions you want to make, it's important to know how to describe a universe that looks like this, because we know it corresponds to our universe, at least for temperatures from a mega-electron-volt until today. So how do we describe a universe in thermal equilibrium? And here, well, I'm going to give you a derivation that it's in the Mukhanov book on cosmology, and I find it very nice because it uses only basic principles, essentially countings of states, to give you the probability distributions of particles in an equilibrium universe, and so it's valid in any geometry. So you don't even need to know that's FRW. Even if it was a completely crazy geometry, my derivation would still be okay. And it all starts from the entropy. So let's say that you label the states in which your system, so the universe, can be in by alpha, and P of alpha is the probability that state alpha is realized. Then the entropy can be written like this. And we know that, well, in a closed and isolated system, the entropy always grows. So you are in equilibrium when entropy reached its maximum value, and you can convince yourself that the maximum value of this function is reached when all the states have the same probability. So when P alpha is equal to 1 over n, where n is the total number of states. And, well, I'm going to call this gamma. Okay, 1 over n is gamma. Okay, so up to here, it seems that we've done nothing. But in reality, okay, in making a couple more steps, we can get to answering the question that we wanted to answer. So what is the energy density? What are the pressure of our universe? So let me call delta and epsilon the number of particles in an interval of energy from epsilon to epsilon plus delta epsilon. Okay, so this is energy. And this is the number of particles in this interval. And then let me call delta G epsilon the number of states of a single particle in the same energy range. Okay. Well, and using the uncertainty principle, I know immediately how to write this delta G epsilon. So it's going to have a factor of G, which are the internal degrees of freedom of the particle. So if it's an electron, it can have spin up or spin down, so this G is going to be 2, for example. If it's a gluon, there are 8 colors, so this number will be 8. But then the rest of the microstates are just summing over your whole phase space divided by the smallest cell that you can distinguish, right? So because of the uncertainty principle, if you have a cell of this size, whatever is smaller cannot be distinguished. So you can only have as many states as there are cell of space of this size. Okay, I don't know if this was clear, but and usually you don't see this explicitly because we always set h/to 1, but the physical meaning of these integrals with the 2 pi cube underneath is this. So this is where the 2 pi cube is coming from. It's coming from the fact that we set h slash to 1 and not h. So if you want pi as dimensions in some sense, it doesn't make, I mean, pi is an important object that you can keep track of using dimensional analysis. Okay, so now with these two definitions, now we can ask the question that we care about. So how many states are there in this interval of energy, which is what we need to know to start computing the entropy. And well, since you have delta G states and delta N particles, essentially you have to ask in how many ways can you put delta N particles into delta G boxes. And this is kind of a standard combinatorial question that mathematicians have answered for us. And the answer is this. So this number is telling us the number of states in this interval. But we want to know the total number of states, not just the number of states in that interval. But the total number of states is just the product over energy of the number that we just got. And this is because, well, so imagine that between epsilon and epsilon plus delta epsilon, you add this delta G epsilon states. Then, okay, you're going to have another interval of energy. And another number of states. But so for each one, you can choose where to put your particles. So at the end, you have a product and not a sum. So you can put any number of particles you want in any one of these states. And then you can put any number of particles you want in any of these states, and so on. So if this was confusing, I tried to write it more clearly in the notes. So I'll try to post the notes tonight, and then tomorrow you can ask me if this is still confusing. But if it's not confusing, now we have what we need to compute the entropy. And so now we have the log of that ratio of factorials. If we are looking at particle with Bose statistics, then this delta N epsilon and delta G epsilon can be big. And so we can expand the log of n factorial for n big using Stirling's formula, which essentially, okay, it's noticing that you can write this like that. And then you can approximate this sum with an integral. And the integral gives you approximately this. So if you want, the logarithm of n factorial grows like n log n. Okay, so we are essentially done. I'm sorry for all these statistics and combinatoric steps, but the same reason that makes them boring also makes them nice, because as I was telling you at the beginning, we are relying on nothing in physics here. So we don't care what's the geometry, what GR is doing. This is just general. We're just counting, nothing more than that. So if we use this formula to compute the entropy, then we're going to get the following result. I hope I did it right, almost. Well, actually I made a crucial sign mistake. And here I'm defining these little n's as the occupation numbers. So essentially it's telling you how many particles there are per state, which if you want, it's what we are interested in, because if we know this, we can sum the energies times them and get the total energy or the energy density, right? So for example, the total energy is going to be a sum over energy of epsilon and epsilon delta G epsilon. The total number of particles is just going to be a sum over energy epsilon delta G epsilon. Okay, so we are essentially done. So now we just have to maximize the entropy with respect to an epsilon and see essentially what functional form of an epsilon maximizes the entropy. And we can do it at fixed energy and number of particles. So we can essentially use Lagrange multipliers to maximize this function and find an epsilon. And I leave you the steps as an exercise. The answer is that an epsilon that maximizes this function is the following. And so we can experimentally investigate a system in equilibrium and determine what are these lambda 1 and lambda 2, and these lambda 1 and lambda 2 turn out to be 1 over the temperature and, so sorry, I should have written epsilon here because I used E for the total energy. So this lambda 1, sorry, there is just lambda 2 and no n. So experimentally, one can show that lambda 1 is 1 over temperature and lambda 2 is chemical potential divided by temperature. So effectively, what we are maximizing here is this object, which, not surprisingly, it's proportional to one of those well-known thermodynamic potentials, so the free energy. So physically, you can think about this in the following way. If the chemical potential is 0, you're paying no penalty for changing the number of particles. If the temperature is infinite, you're paying no penalty for changing the energy of the system. Okay? This is kind of a crazy limit, but it's intuitive why. So if you have infinite temperature, you can add energy to your system for free. And this is what this potential is telling you. So it's telling you how you're spending your thermodynamic energy. And you can repeat all these steps for fermions. This time, you're not going to expand the logarithm of the factorial when these guys are large, but you're going to write it when delta G can only be 0, sorry, when delta N can only be 0 or 1. And if you do that, and again, I leave it to you as an exercise, you're going to find essentially the same expression here, but the fermions have a minus. And in the end, you're going to find also the same n epsilon, only with a plus. And even though at the moment it doesn't look like it, we essentially have arrived at the answer. So we wanted to know what's the energy density and the pressure in a universe full of particles in equilibrium. And now we know, because this is the energy. So if you want the energy density, it's C over the volume. So it's going to be that quantity over the volume. And we can just plug in the definition of delta G epsilon down there at the very opposite side of the lecture room. And we're going to have now I'm setting h slash to 1. There we go. So to get to our goal, we need just to do an integral. So the integral over the position is giving us a volume, because this n epsilon is independent of position. And notice that we didn't even use isotropy or homogeneity. So we didn't even need to use our symmetries. We didn't need to use translational invariance or rotational invariance. The fact that n depends only on energy came just from the requirement of being in equilibrium. So you see how powerful equilibrium is. It's as powerful as rotational plus translational invariance. Okay, so now you just have to translate the integral over momentum to an integral over energy. So, sorry, I forgot a g from delta g epsilon. So essentially, in the end, you're going to get g over 2 pi squared times so this is the answer for the energy density. For the pressure, you have something very similar, but, well, for the number of particles, oh, sorry, I forgot an epsilon here. For the number of particles, you have the same without this epsilon. And, well, OK, one can show, and I suggest you look at the book by Mukhanov or Kolben-Turner, that the pressure can be written in terms of the energy density and the number of particles in the following way. So now we have all the quantities we needed, but we don't have a lot of intuition on how they look like, because we have these, well, these integrals are one-dimensional, so in practice they're something that you can easily do numerically or in many cases even analytically. But let's see what all this stuff means in terms of a bit more manageable quantities. And so let's say, for simplicity, that there was only one particle species. How much time do I have? 5 minutes? OK. Well, I did, OK. Maybe I did better than I thought, but much worse than I should have in terms of quantity of stuff. OK, so if I have 5 minutes, I'm going to tell you the last thermodynamics facts about these integrals. And then we're going to do WIMPs tomorrow. OK, so we started from the FRW metric, and we asked how the scale factor evolves. This led us to Einstein's equations. Then we, based on very general principles, we wrote T mu nu for a collection of particles at rest. And then we were led to ask what these objects look like in thermal equilibrium because of what we know experimentally of the universe. And now we know these objects in thermal equilibrium. They are these integrals. And so let's see what they look like. So let's say that the temperature was much larger than all the masses of your particles in the game. In this case, you can expand the exponentials in these integrals, and you're going to get that the energy density goes like t to the 4th, and the pressure like t cube, and the number of particles also like t cube. And it is something that you could actually have guessed from the beginning, because if t is much bigger than all the masses, it's the largest dimension full scale in your problem. Rho, as you can see from this expression, or even more simply from ER, as dimension of energy to the 4th. And where is it? Little n as dimension of energy cube. So these are the only possible scalings. Same for the pressure. What these integrals instead are telling you, so this fact you could have known without doing any of the exercises of the lengthy derivation that we did. But the integrals are telling us something important in the opposite regime. So what happens when T is much smaller than the mass? And let me say that also the chemical potential is small for the moment. So in this case, from, again, expanding these integrals, you're going to get that all these quantities are exponentially suppressed. Okay? Of course, they have different factors in front, but the important part is that they always have an exponential suppression from the denominator. And again, in the notes, you will find more precise expressions. So this is telling us that if the universe is expanding and cooling down, as you probably have seen already with J, but if not, I will tell you tomorrow, then initially everyone is light with respect to the temperature and is contributing to the total energy density. But then at some point, massive particles become irrelevant. So essentially, the total energy density of the universe is dominated by light particles. And since Hubble is proportional to the total energy density in the universe, so Hubble squared, the other terms we know experimentally that are negligible. So we know that the curvature and the cosmological, so the curvature is 0 and the cosmological constant became comparable to the energy density of the rest of the stuff only today. So the expansion of the universe, if you remember, this is A dot over A, is determined by the total energy density that we just estimated. And this is telling you that particles that are massless compared to the temperatures dominate. So you can always write down Hubble in the following way. So you can write down Hubble as so for the vast majority of the history of the universe, this is going to go like T to the 4th over m Planck squared, so Hubble squared. This G star is counting how many particles are light. So it's just a sum over bosons times the number of internal degrees of freedom, their temperature over the temperature. So when I write T without any subscript or superscript, I mean the temperature of the photons, which are massless, so they will remain important forever. So we measure everything relative to the temperatures of the photons. And there is a sum over fermions. Well, there is a order 1 number, but it's the same. OK. Yeah, so there are a couple more things of this basic thermodynamics that I'm going to tell you tomorrow. But to conclude on an interesting note, well, what we derived today essentially is that a universe in equilibrium is a dead universe. Because at some point, well, we didn't derive it completely because we didn't solve Friedman's equation. But you solved it with J, and you can also see it from here. So you see that if you have a positive energy density, the universe is expanding. And one can then show that if the universe is expanding, the temperature is decreasing. So a universe in equilibrium will start with some temperature, and then will become larger and larger and colder and colder. And at some point, everything massive will be a negligibly small amount of the total. So if the universe had always been in equilibrium, it would be a featureless, nameless vat of photons. But clearly it's not, because we're talking today. And so tomorrow we're going to see how to describe departures from equilibrium in a Boltzmann equation. And immediately after, we're going to see how this can give us a very simple and predictive dark matter candidate. And after that, we are actually going to talk about light stuff. So this simple and predictive dark matter candidate is going to be heavy in the traditional sense. And then we're going to compare its qualities and drawbacks to qualities and drawbacks of light dark matter candidates. OK, so thank you very much. Sorry for running a bit long. That's OK. 1 hour and a half with no stops, it's tough.
Okay, well, Raffaele and all the other lecturers are here the entire week,
Yes.
so let's thank Raffaele again. And we'll come back at 4 o'clock.